A very good morning, ladies and gentlemen. I'm Kohmalam Ayanasamy, currently pursuing my master's in UMP. As a co-inventor, I'm here to present our research study titled Reducing Sugar Production from Hydrolysate of Pineapple Residues via Integrated Enzyme-Membrane System. I would like to thank the organizers and all the sponsors to provide me this opportunity. Let's move to the introduction. Lignocellulosic biomass is an attractive feedstock for numerous biorefining processing technologies due to its low cost, abundance, and widespread availability. Lignocellulosic biomass refers to agricultural waste and it's an alternative to petroleum. This kind of waste usually eliminated by burning, which leads to environmental issues. Due to these issues, concern on the effect of burning crop waste have been expressed, including pineapple leaves burning. Utilizing pineapple leaves to produce value-added products can minimize waste and reduce environmental pollution. Pineapple leaves made out of cellulose, hemicellulose and lignin. For hemicellulose degradation, there are different hydrothermal processes like acid or alkaline hydrolysis, ozonolysis or steam explosion. However, few drawbacks such as relatively low yield, high temperature, and formation of undesirable product shifted the option to enzymatic hydrolysis. The structure of hemicellulose can be converted to monosaccharides by specific enzymes called hemicellulase. Meanwhile, the nanofiltration process can recover fermentable sugars and remove unwanted components due to its ability to separate small molecules and salts. The objective of this study is to find the best pH, temperature, enzyme loading and reaction time for maximum reducing sugar production using enzymatic hydrolysis, and also to investigate the reducing sugar production by enzyme membrane integrated system. The overall workflow starts with collection of lignocellulosic biomass, followed by preparation of lignocellulosic hydrolysate via hydrothermal pretreatment, and evaluation of enzymatic hydrolysis via OFET method at different working conditions, evaluation of hydrolysis and separation performance simultaneously, and finally with reducing sugar analysis via DNS method. As for the methodology, the initial step was to find the best operating condition for pH. Three pH levels of 4.5, 6 and 7.5 were investigated. The pH values were chosen based on the optimum pH range found in previous studies. 5 molar of sodium hydroxide and 5 molar of sulfuric acid were used to achieve the required pH. For the effect of temperature, 3 different temperatures, that is 40, 50 and 60 degrees Celsius, were tested. The best enzyme loading was identified by comparing 3 different enzyme loadings, which are 0.5%, 1% and 2% weight per volume. Lastly, the effect of reaction time was investigated at three distinct time intervals, which is 15, 30 and 45 minutes for the hydrolysis reaction. For the enzyme membrane integrated system experiment, an F270 membrane was utilized. Following the manufacturer's recommendations, the membrane was first soaked in 50% ethanol solution for a small duration of 10 seconds before being rinsed with distilled water. After that, the water permeability was tested using distilled water at 4 bar. The best enzyme loading achieved earlier through enzymatic hydrolysis by beta-xylosidase was added to the solution in the amicon stirred cell, since the enzymatic hydrolysis had to be conducted at the best temperature for the enzymes. 250 rpm was used to agitate the solution. Before recording the filtration time, the initial drops of permeate were discarded and aliquots of 10 ml permeate were collected. To stop the reaction, the enzymes in the retentate were deactivated by heating at 100 degrees Celsius for 10 minutes in a water bath. The residue on the membrane was washed multiple times with distilled water after the retentate was removed, and then water permeability test was repeated to determine the permeability loss. This is the results of effect of pH on enzymatic hydrolysis for production of reducing sugar. pH 7.5 gave the best results, with maximum concentration of reducing sugar being 1.44 gram per liter, which was higher than pH 6 and 4.5 respectively. For most enzymes, extremely high or low pH levels results in a total loss of reaction. This is because alterations in pH cause the ionic bonds that bind the tertiary structure of the enzyme together to break, affecting the overall net charges of the enzymes. As a result, the enzyme begins to lose its functional form, notably the shape of the active site, causing it to be denatured and incapable of catalyzing chemical reactions. The rate of reducing sugar production will decrease as the rate of hydrolysis decreases. Other research found that the best pH working conditions for beta-xylosidase were between pH 6 and 7. In this study, it was found that the best pH for beta-xylosidase is at pH 7.5. The results shows the effect of temperature on enzymatic hydrolysis for production of reducing sugar. The highest reducing sugar production was recorded at 50 degrees Celsius. The enzyme must collide and bind to the substrate's active site in order to convert the hydrolysate into reducing sugar. A rise in temperature generates enough energy to provide a proper collision orientation. As a result, when temperature increases, the rate of reducing sugar production increases. Thermal denaturation can lower an enzyme's activity at higher temperatures, resulting in a reduction in the hydrolysis rate. At high temperatures, enzymes become inactive due to the unfolding of their structures. The trend shown in this study is compatible with those hypotheses. The results of effect of enzyme loading shows the highest reducing sugar concentration was recorded at enzyme loading of 1% weight per volume. The sugar production was initially increased and then plateaued as the enzyme loading increased. The reaction was initially accelerated as more enzymes were present to hydrolyze the fibers, but afterwards began to slow down at one point when higher enzyme loading became in access to the substrate. Initially, the enzyme adsorbed on the substrate forms a single layer, with the excess enzyme adsorbed forming additional layers subsequently. This has reduced the diffusion of excess enzyme from the substrate surface. Based on the results, enzyme loading of 1% weight per volume was sufficient to hydrolyze the polysaccharides as it gave the highest reducing sugar production. Adding more enzymes to the process would be impractical because the yield has already reached its maximum. Therefore, 1% weight per volume of beta-xylosidase was used in the following experimental work as it would reduce the operational cost. The results of effect of reaction time shows the highest reducing sugar concentration was recorded at reaction time of 30 minutes. The longer the enzyme is in contact with the substrate, the greater the amount of product that should be formed. However, the rate of formation of sugar obtained is not a simple linear function of the reaction time. The low sugar concentration at 15 minutes could be caused by the shorter interaction time between enzymes and substrates. Meanwhile, the difference between 30 and 45 minutes was less significant, which might be due to the enzyme reaction being limited by the production of reaction products at high degrees of hydrolysis as the time increases. Due to a lack of substrate, enzyme inhibitors and enzyme deactivation, the hydrolysis efficiency may be reduced. The best working conditions obtained in enzymatic hydrolysis part was used for the simultaneous reaction and filtration experiment. The experiment was carried out at pH 7.5, 50 degrees Celsius, 1% weight per volume of beta-xylosidase and filtration pressure of 4 bar. Based on the results obtained, the concentration and yield of reducing sugar produced for the reaction only were 1.44 gram per liter and 32.23% respectively. Reaction only shows significantly lower sugar production compared to the simultaneous reaction and filtration system, which has produced 4.29 gram per liter of reducing sugar with a yield of 293.94%. The results indicate that reducing sugar production can be significantly improved by integrating the membrane with enzymatic hydrolysis. The molecular weight cutoff of the nanofiltration membrane used was 150 Dalton on average. With a molecular weight of 150 gram per mole, the smallest monosaccharide is xylose, whereas the acids and other inhibitors in the feed solution range from 40 to 120 gram per mole. Thus, the nanofiltration membrane therefore retains the sugars but allow other harmful compounds such as furans to pass into the permeate. As a result, the concentration of xylene oligomers on the membrane surface gradually increased. On the other hand, sugar concentration as a function of time indicates that the concentration increases with time. In conclusion, the enzyme membrane integrated system produced almost triple the amount of sugar produced by enzymatic hydrolysis at similar working conditions. Therefore, reducing sugar production can be significantly improved by integrating the membrane with enzymatic hydrolysis. As for future perspective, further study has to be focused on enzyme membrane system configuration. Besides, enzymatic hydrolysis can be performed by combining enzymes such as a cocktail of beta-xylosidase and xylanase, since xylanases break the primary chain of xylene and liberate xylo-oligosaccharides, which are then degraded to xylose by beta-xylosidase. This research was funded by University Malaysia Pahang and the Ministry of Higher Education of Malaysia. A big gratitude also goes to Pekan Pina Sendirian Berhad for providing pineapple residues as raw material to complete this research. Thank you.